Hi everyone, our lesson today is permutation without replacement, repetition or return using this general formula which we are going to derive using this problem here. Assume a set of 4 distinct objects A, B, C and D. We are going to place this object in the urn and we are going to withdraw them according to these 3 rules. The first one, we are withdrawing these objects in 2 consecutive turns. And the second one, we are not going to return any object after each withdrawal. And the last one, we are going to withdraw these balls in order. So we put all the 4 objects in the urn and we start the first withdrawal. Let's say we have withdrawn ball number 2, we place it outside, and now the urn has 3 balls only. We mix these balls before the second withdrawal to make sure that the withdrawal event is random one. And we start again. Second withdrawal, we are withdrawing ball number 1 for example, we are placing it outside, and now we get the sequence 2, 1. Now the urn has only 2 balls, and we can repeat this cycle over and over again to generate a new sequence such as 2, 1, 3, 4, and so on. But every time we start this experiment, we have to refill it again with the 4 balls and start again. So all this process is one withdrawal cycle to generate one random sequence such as 2, 1. If we repeat this cycle over and over, we may get in cycle 2, 4, 3 sequence. In cycle 3, we may get sequence 1, 2, 4, 3, 2, 4, and so on. So now we are interested in knowing how many possible outcomes we may get out of this experiment, or the sample space. So we are going to use the tree diagram using these 3 rules. We are going to withdraw only twice. So in the first withdrawal, we may get object number 1, 2, 3, or 4. And assume that we have withdrawn number 2, so now number 2 is no longer available in the urn. So in the second withdrawal, we are going to get 1, 3, and 4 excluding object number 2. So now we want to know all the possible outcome. Let's say 3 and 4 is referring to one possible outcome here. We may withdraw 2 and 1, and we have possible outcome 2 and 1. And so on. And now we need to find the mass formula for the number of possible outcomes of this experiment. So what we do is we divide this mother tree into 4 subtrees and we write down the number of each outcome in each subtree. So now we have for the first subtree we have 3 outcomes, for the second one we have 3, and so on. We add them together and we get 4 times 3. We write 4 times 3 as a fraction. We multiply the numerator by 2 times 1 and we multiply the denominator by 2 times 1. We notice that 4 times 3 times 2 times 1 is 4 factorial, and 2 times 1 is 2 factorial, which can be written as 4 minus 2 factorial. So now we arrive at this fraction where 4 is n, the number of objects in the sequence, and 2 is the number of withdrawal or the size of the sequence. And now we can write it in a formal form like this, and we arrived at the permutation formula P(n)(r) equal to n factorial divided by n minus r all factorial. We read this formula P(n)(r), where P is permutation, which implies order, and without replacement. We write nothing here in the notation to indicate that it is without replacement. If we write R here, it means permutation with replacement. Or we call it permutation without repetition, and without repetition means that no symbol or no object is going to be repeated more than once. So we are not going to find, let's say, DD when we permute A, B, C, D, E 4 times. We are not going to find DD in the sequence at all. Or we call it permutation without return. For n different objects taken R at a time, where R is sequence length, so number of symbols in the sequence. Whether they are objects or symbols, all means the same. So we read P and R as permutation without replacement of n different ordered objects taken R at a time. We may find in some other books or references, we may find it written as P in parentheses n comma R equal to n factorial divided by n minus R all factorial. So now we need to know the conditions according to which we have to apply this formula and the definition of all the parameters. So n is number of objects in the set, or number of objects we are going to permute, and R is the length of the generated sequence, which is the number of symbols in the sequence. Now the conditions are, to apply this formula, we have to make sure that these conditions are available, otherwise we are going to make a mistake. The first condition is all objects are ordered. The second one, we are withdrawing without replacement, and the third one, R ranges from 1 to n as a natural number. So 1 is in between 1 and n, including 1 and n. So if R is equal to 1, then we are having here permutation of n different objects taken one at a time, and we know that is going to be n. And if R is equal to n, then we are going back to the old formula, which is permutation of n different objects taken n at a time, and this is equal to n factorial. Now we notice that n minus n is 0, and 0 factorial is defined as 1. We can also compute the number of all possible outcomes by writing the withdrawal event in order, and for each event we write the corresponding number of occurrences. So for withdrawal 1, the first withdrawal we have 4 ways, and for the second withdrawal we have 3 ways. We multiply them together and we get a 12, which is the number of all possible outcomes, which is permutation of 4 different objects taken 2 at a time. There is only one notice before we leave. Assume we have this permutation formula, and we are going to substitute n equal to 4, r equal to 2. So we are going to get 4 factorial divided by 4 minus 2 factorial, and we can use that in the calculator immediately, or we can expand it and use a multiplication process only. But usually for something small like this, we can do it in a shorter way. We can write permutation 4 taken 2 at a time as multiplication of 4 times 3 immediately, without resorting to this previous formula. That's if the permutation is being calculated for small numbers, let's say permutation of 4 and 2, or permutation of 7 and 3. So now we start from 7, we multiply 3 times in descending order, and we can compute that immediately. If we have permutation of 100 for 37 times, then it is really better to use the calculator in such case. But for small numbers like this, we can just do them immediately by multiplying these numbers 3 times, and we can get the answer immediately. Thank you for listening, and have a good day.